Foundations of Arithmetic. Understanding numbers, basic mathematical operations, and decimal systems. Mathematics is a universal language that helps us understand events in the universe. Let's delve into some fundamental concepts of this language, from arithmetic to algebra, and up to geometry. Today, on the Infinite Science channel, we're exploring these crucial parts of basic mathematics. Equations and inequalities. Understanding the basics. Equations frequently appear in mathematics. They are mathematical expressions that show the relationship between variables. Consider a simple equation like x plus 5 equals 10. In this case, we need to find the value of x. To solve such equations, we perform the same operation on both sides to keep the equation balanced. In this instance, by subtracting 5, we find that x equals 5. Another critical topic is inequalities. Inequalities indicate that two expressions are not equal, meaning one is greater or less than the other. Take the inequality 2x is less than 8. Here, we need to determine for which values of x this expression holds true. By dividing both sides by 2, we find that x is less than 4. This means the inequality is true for all values of x less than 4. An essential note regarding inequalities is that the direction of the inequality can change when multiplied or divided by a negative number. For example, consider the inequality negative x is greater than 5. When dividing by x, we need to flip the direction of the inequality, resulting in x is less than negative 5. With this foundational knowledge, we've taken a step forward in understanding equations and inequalities. These concepts are of paramount importance as we delve into more advanced mathematical subjects. Number systems, decimal, binary, and beyond numbers can be represented in various ways. These methods form the number systems we use. Perhaps you're familiar with the decimal system, using it daily, but what about the others? The binary system, the hexadecimal system. These systems play a significant role not just for mathematicians or computer engineers, but for anyone deeply involved with technology. To start, we need to understand what a number system fundamentally is. Number systems are methods used to represent and record numbers. Each number system has a base. This base specifies the number of different digits used in that particular system. Let's begin with the decimal system. This is the system we use most frequently in our daily lives, and its base is 10. This means we use a total of 10 digits, ranging from 0 to 9. But why 10 digits? The fact that humans have 10 fingers might have played a significant role in the historical adoption of this system. As technology advanced, computers and digital systems entered our lives. Computers operate using electrical signals, necessitating the use of the binary system, that is, a system with a base of 2. In the binary system, only the digits 0 and 1 are used. This forms the fundamental language of a computer. An electrical current is represented as 1, and its absence as 0. However, these two aren't the only number systems. For instance, there's the octal system with a base of 8, and the hexadecimal system with a base of 16. In the hexadecimal system, instead of just the digits 0 through 9, letters from A to F are also used. This system is particularly prevalent in computer science and programming. So, why are there so many different number systems? Each has been developed to address specific problems or to be more efficient in particular applications. For example, while the binary system is ideal for electronics, the decimal system is more suitable for general computations. Basic mathematical operations, addition, subtraction, multiplication, and division. From the dawn of history, mathematics has employed 4 fundamental operations: addition, subtraction, multiplication, and division. These operations play a foundational role not only in basic computations but also in advanced mathematical analyses and theoretical concepts. Addition: it is the combination of 2 or more numbers. This concept, developed with contributions from Arab mathematicians and previous civilizations, is especially used in summative series, integral calculus, and vector analysis. Mathematically expressed as a plus b equals c. For example, 2 plus 3 equals 5. The addition operation holds significant importance in group theory and abstract algebra. Subtraction, it refers to the removal of one number from another. Subtraction can also be thought of as the inverse of addition. Differential calculus and error analysis are closely related to this operation. It's represented formulaically as a minus b equals c. 7 minus 4 equals 3. This means when you subtract 4 from 7, the remainder is 3. Multiplication. It's the new value formed as a result of the interaction between two numbers. Historically, the multiplication operation is fundamental for the analysis of large numbers and long sequence numbers. It plays a pivotal role, especially in linear algebra matrix multiplications and certain operators in quantum mechanics. It's mathematically represented as a times b equals c. 4 times 3 equals 12. Taking 4 3 times gives 12. Division. It's the quotient obtained when one number is divided by another. Division helps us understand ratios and proportions in mathematics and is fundamental in the analysis of fractions and rational numbers. In math, it's denoted as a divided by b equals c. For instance, 12 divided by 4 equals 3. This shows that the result of dividing 12 by 4 is 3. These four basic operations form the foundation of mathematical concepts. Functions, differential equations, complex numbers, and many other mathematical fields rely on understanding these four operations. Therefore, a deep understanding of these fundamental concepts is essential for transitioning to more advanced and complex topics in mathematics. Order of operations in mathematics. Mathematics is filled with nuances that ensure consistency and accuracy, and one such nuance is the order of operations. It's the subtle hero behind why we all, no matter where we are in the world, get the same results when working on mathematical problems. When faced with mathematical expressions that combine addition, subtraction, multiplication, and division, we don't simply compute from left to right. There's a specific sequence to follow, ensuring uniformity in results. Many remember this sequence through the acronym PEMDAS, which stands for parentheses, exponents, multiplication and division, from left to right, and addition and subtraction, from left to right. A quick breakdown. 1. Parentheses. Tackle whatever's inside parentheses first. This can also refer to brackets or other grouping symbols. 2. Exponents. Think powers or square roots. 3. Multiplication and division. These are tackled from left to right. If division appears before multiplication, you divide first. 4. Addition and subtraction. Similarly, these are performed from left to right. For instance, in the expression 6 plus 2 times 3, using the order of operations, you'd first multiply 2 by 3 to get 6, and then add to the other 6, giving a total of 12. The order of operations isn't just a set of rules. It's foundational for ensuring that mathematical expressions are universally interpretable. Just as every language has its grammar, in the world of numbers, the order of operations is a pivotal grammar rule. Understanding percentages, fractions, and decimal conversions in our daily lives, numbers in various forms surround us. Whether you're tipping at a restaurant, measuring ingredients for a recipe, or analyzing data, understanding percentages, fractions, and their relationship with decimals is crucial. Percentages are everywhere, from discounts in stores to interest rates in banks. The word percent literally means out of 100. To calculate a percentage, you divide the portion by the whole and then multiply by 100. For instance, if 15 students in a class of 30 have glasses, 15 divided by 30 is 0.5. When you multiply by 100, you get 50%. So, half of the students, or 50%, wear glasses. Now, let's talk about fractions. At their core, fractions represent parts of a whole. The number on the top is the numerator, indicating the portion, and the one below is the denominator, indicating out of what total. Continuing with our example, 15 students with glasses out of 30 is represented as the fraction 15 over 30, which can be simplified to 1 over 2 by dividing both the numerator and the denominator by their greatest common divisor. But how do fractions relate to decimals? Well, a decimal is just another way to represent a fraction. Our simplified fraction 1 over 2 can be converted into a decimal by dividing 1 by 2, which gives us 0.5. This conversion between fractions and decimals is what bridges the gap to percentages. As you saw earlier, 1 over 2 became 0.5, which was 50%. So, the path is clear. Fractions can be converted to decimals, and decimals can easily be translated to percentages by multiplying by 100. Percentages, fractions, and decimals are interrelated tools to express parts of a whole. Understanding their relationships and conversions between them provides clarity and precision in various real-world situations. As you continue your mathematical journey, these foundational concepts will become second nature, equipping you with the skills to tackle more complex problems with confidence.